Hello, everyone. Thanks for attending. My name is Cai. Today, I'm going to present our work on fast non-blocking persistence for concurrent data structures. The work is done by me and my colleagues from the University of Rochester. The new technology of non-volatile memory allows us to keep pointer-rich in-memory format data structures in memory so that we can reuse them across executions, even with crashes. However, since caches remain volatile, at least on the current machines, and write back to memory can be out of order, we need to properly issue expensive hardware instructions like cache line flush and fence to ensure the post-crash data consistency. Those instructions write back specific cache lines and wait for their completion. In 2016, Relevance et al. Introduced durable linearizability, a criterion that builds on linearizability of concurrent transient data structures. This criterion, however, requires operations to become persistent before their response, which implies at least one flush and fence in every operation. This results in high overhead. In the same paper, they also introduced a buffered variant of the criterion, which allows multiple operations to be flushed in batch, followed by a single fence, with a trade-off of possibly losing a small suffix of the history after a crash. This allows more relaxed order of write back and therefore much lower overhead. In 2017, Nawab et al. Proposed periodic persistence, a design paradigm for buffered durable linearizability. This divides time into epochs and persists operations starting in the same epoch in batch. Specifically, an epoch advance from E+1 to E+2 waits and flushes operations starting in E. By doing so, every epoch boundary represents a consistent cut of the history. Here is an example to illustrate the idea. Operation 1 and 2 start in epoch E. With time goes by, the global epoch ticks over to E+1, and the system decides to advance epoch to E+2. The epoch advancer then waits for all operations from E to finish so that it can flush their updates and move forward. At the same time, the system may allow operations like operation 3 from E+1 to continue, as long as it doesn't linearize after an operation from a new epoch. Suppose in E+2, we hit a crash. Then, during recovery, we drop the most recent 2 epochs and get a consistent prefix. Based on periodic persistence, Wen et al. Introduced Montage, the first general-purpose system for building buffer durable linearizable data structures. To leverage the hybrid memory hierarchy and reduce the number of writes back, it separates transient indexing and persistent payloads. This figure shows a persistent hash table built using Montage. The blue part represents the transient indexing, which are a set of buckets, each of which contains a linked list of keys. They are transient and can be rebuilt during recovery. The red part represents the persistent payloads, consisting of key, value, unique ID, and epoch number. These persistent payloads either linked into the indexing or not. There is also a special kind of persistent payloads called anti-payloads, which indicate that their corresponding payloads have been deleted. When the transient part of a deletion is done, we create an anti-node against the payload. As optimization, a payload created in some epoch can be updated in place with the same epoch. Updates on a payload from an old epoch creates a new payload and swap it into the indexing. The system has a dedicated thread that periodically decides to advance the epoch. It will wait for operations from the old epoch to finish and flush their payloads. The user may also call sync to explicitly ask the dedicated thread to advance the epoch in order to make sure that every operation before the call has been persisted. When crash happens, the transient indexing is gone, and payloads from the most recent 2 epochs are thrown away. And based on the leftover persistent payloads, we will rebuild the transient indexing. To support non-blocking data structures, there are 2 cruxes. First, Montage inherits the design of blocking persistent data structures from the original periodic persistence paper. In order to ensure that the linearization order of operations still obeys the epoch order, Montage uses old see new exception to prevent dependency on an operation from a new epoch. Blocking operations may acquire the exclusive access to prevent such exception, or if the exception arises, they may roll back their changes while holding the lock. However, non-blocking operations cannot acquire exclusive access, so they can't prevent or handle old see new exception like blocking ones. We need another way to obey the epoch order. Second, and most importantly, the Epoch Advance in Montage has to wait all operations from 2 epochs ago to finish. This suggests the blocking progress of the persistence frontier and blocking sync. In other words, it's impossible to bound the loss on a crash. Now, we're starting to talk about how to solve the crux and build non-blocking periodic persistence. First, to let linearization order obey the epoch order, we observe that non-blocking operation has to linearize in the exact epoch in which it begins. If it goes beyond its epoch, we cannot guarantee the linearization order anymore, so it has to fail. To ensure this, we replace plain cas used to linearize the non-blocking update with a software double compare single swap primitive that also verifies the epoch. Second, because of the observation, the weighting mechanism in Montage is unnecessary for non-blocking data structures anymore, which, as we mentioned in the last slide, is the source of blocking persistence. Unfortunately, this weighting mechanism is deeply embedded in Montage. So, to fully support non-blocking data structures and provide non-blocking persistence, we redesigned Montage, breaking the weighting mechanism and get a variant called NB Montage that provides weight-free progress of the persistent frontier and easy-to-use API tailored for non-blocking data structures. Just like Montage, it also provides sync operation for persisting everything before that call, but this time it's more responsive. Even more, NB Montage keeps the great performance with just negligible overhead to the original Montage. to break the fundamental waiting mechanism and enable non-blocking Epoch Advance, there are 4 challenges we need to address. First, pending updates must be staged but invisible to other workers before linearizing, so that Epoch Advance may still persist them even if an operation stalls immediately after it linearizes. In this challenge, we will discuss API changes that enable pre-staged updates. Second, recovery procedure needs to distinguish between linearized and failed operations. In this challenge, we employ some reusable, persistent operation descriptors to direct the post-crash recovery. Third, those doomed threads may still work in some arbitrarily old epochs, and the system should tolerate this. In this challenge, we redesigned the buffering containers. In particular, we designed a single producer, multiple consumer circular buffer that intentionally allows duplicated pops on the same item for better performance. And finally, we want to make Epoch Advance fully non-blocking and ideally fast. In this challenge, we leverage a locality-aware lock-free binary tree for collaborative Epoch Advance. Now, let's consider each of these challenges in detail. The key NB Montage API is as follows. pnew and pdetach creates a payload and anti-payload, respectively. When it is safe, the user may also call pdelete to reclaim the memory space of a removed payload and its anti-node. Lincast is to replace the plain linearizing cast. It verifies the epoch and casts on the object atomically. Specifically, to allow operation to stage all updates before linearizing, we abandon in-place updates and ask every operation to express their semantics by either pnew or pdetach and publish it using the lincast. Payloads created by these calls are staged and are only visible to Epoch Advance before linearizing. In lincast, those staged payloads are tagged with the newly fetched epoch. Based on the fetched epochs, the advancer respects them accordingly, even when their parent operations stall immediately after linearization. Okay, so now we have payloads and antinodes written back. But during recovery, we have to identify only effective ones. To do so, we employ a set of persistent descriptors, one per thread. They consist of cast parameters, epoch, status, in addition to unique operation ID, consisting of thread ID and a monotonic serial number. Each payload corresponds to one operation ID. Every lincast increments the thread's serial number to make operation ID unique for all attempts. Once serial number increments, previous operations by this thread will be considered as committed. This works as long as we reset blocks of failed updates before next attempt. This way, we recover, the recovery may identify all and only in-use blocks according to payloads and descriptors, operation ID, and status. Those doomed threads may continue working in an arbitrarily old epoch before noticing, while others may have started pulling things from their buffers already. To tolerate this, we modify the buffering containers while keep their original design of just 4 slots per thread. First, the single-threaded buffer for holding to-be-persisted payloads is redesigned to support single producer, multiple consumer access. For performance, we intentionally allow to-be-persisted buffers to pop an item more than once. Here, duplicated pops only result in duplicated flushes on the same cache line, which are harmless. On the other hand, we don't need to handle the buffer for holding to-be-freed payloads by some exact epoch. So we decentralize the handling to each thread and let them do it lazily. Specifically, when initiating a new operation, the thread checks its to-be-freed buffer and handles deletions from previous epochs. Since this thread doesn't perform anything between the epoch of its last operation and the current operation and the current epoch. So despite the arbitrary number of epochs between each handling, every time a thread needs to handle only a bounded number of to-be-freed slots. Specifically, this bound is 3, and 4 slots are more than enough. To make Epoch Advance non-blocking, we first decentralize it to caller threads. So there's no need to wait the dedicated thread to proceed and respond, which was essentially blocking. To lower the Epoch Advance latency, or we'll say to amortize the latency, we employ Mindicator to track the oldest, still not persisted epoch. This is a weight-free, fixed-size, locality-aware balanced tree. Each leaf represents a thread and the epoch this thread is currently in. The epoch number in each node indicates the minimum epoch in its subtree. During Epoch Advance, the caller scans up and down in the tree from its leaf to find and persist lagging threads. Of course, a single thread may finish all the work, but this strategy of starting from its own leaf leverages the locality awareness and enables collaborative sync. This, in practice, improves the performance, especially when there can be more than one cause to sync concurrently. This way, sync takes only a few microseconds to finish on average. So in the experiments, we use Intel processor with 20 physical cores and 40 hyperthreads, 6 channels of 128 gigabytes Optane DIMMs, and 6 channels of 32 gigabytes of DRAM. Here, we only show results on hash tables, but we've transformed many transient non-blocking data structures to be buffered persistent using NB Montage. Those are including queues, trees, and skip lists. Those results are covered separately in the paper. This figure shows the throughput of NB Montage comparing to Montage, other persistent competitors, and the original transient non-blocking hash table. The red line and the pink line represent NB Montage and Montage. Solid lines represent persistent structures, and the dotted lines are transient ones. As we know, as you can see, the red line and the pink line are almost together, meaning that Montage and NB Montage are very, very close. They both outperform most of the state-of-the-art non-blocking persistent competitors, except soft, which is faster because it duplicates keys and values as a fast pass on DRAM and never read from NVM copy, except during recovery. NB Montage is also close to the transient hash table allocated on NVM, and and its performance remains more than a half of DRAM's version. In another experiment, we tested the average latency of sync in different sync frequency. With sync being called less frequently, the latency of each sync in Montage increases exponentially, while in NB Montage, it's relatively stable, and more importantly, as much as 2 orders of magnitude lower than Montage. In conclusion, based on Montage, we build NB Montage as the first general system for non-blocking periodic persistence. It preserves lock freedom of persisted structures and provides weight-free Epoch Advance. The code of NB Montage and transform data structures are all publicly available at this link. That's all. Thanks.